Hi, my name's Olaf Krugolson, and I'm that neuroscience guy. In this video, I'm going to help you understand the output of an FFT transform in MATLAB. I'll start by creating a sine wave, and I'm going to define that sine wave in terms of a sampling rate, which is set at 1,000 here. I'll define a time step, or the period of the signal, which is just 1 over the sampling rate. I'll create a length of time, or define a length of time for the signal to exist, which is 1 or 1 second, presumably. I'll create a time vector then, and this is the time vector over which the signal will be built. I'll define the number of data points, which is just the length of the time vector. Then I'm going to give my sine wave an amplitude of 5 and a frequency of 15 hertz, and then I'm going to create my sine wave. I'll use subplot here just because I'm going to create some other waves, and I want to show you how they all fit together. What you'll see is I've created a sine wave, and now let's run an FFT and look at the output. So running an FFT in MATLAB is relatively trivial. You just use the FFT function and pass in a waveform, and that will get you Fourier coefficients. So let's do this and take a look at the output. The FFT gives you an output which includes both positive and negative frequencies. Now, in the case of a real signal, like an EEG waveform, for instance, the signal is entirely real. Therefore, the negative frequencies don't really have any meaning. But I'll show you there, because if you just run the FFT the way they did, you will see these positive and negative frequencies. Now, in terms of interpreting the output of an FFT, another point that you need to note is that the number of Fourier coefficients that are provided is equivalent to the number of points in the waveform. So if your waveform has 1,000 points in it, you'll get 1,000 Fourier coefficients. And if your waveform has 5,000 points in it, you'll get 5,000 Fourier coefficients. To prove this, let's create a second waveform that's just 5 times longer and run it and look at the plots. Let's first of all look at the MATLAB workspace. What you'll notice is the first waveform does indeed have 1,000 time points. The second one does indeed have 5,000 time points. And if you look at the Fourier coefficients, you'll notice that there's 1,000 and 5,000. So the number of Fourier coefficients, like I stated, is equal to the size of the input waveform. Another thing to notice here is that the output is complex. Here's the way a Fourier transform actually works. What the Fourier transform does is compute the dot product between a series of complex sine waves that have both real and imaginary components and the data. And because of that, the output is complex. It has both real and imaginary components. You can actually see proof of that in the MATLAB command window, because the MATLAB, when it tries to plot the Fourier coefficients, is telling you that it can only plot the real component and it can't plot the imaginary component. Now, looking at the plot, what you'll notice is the plot on the left has 1,000 data points and the plot on the right has 5,000 data points, which is exactly what we'd expect given the data that we put into the Fourier transform. Another thing you should note is that the output has different amplitudes. If you look at the two bottom figures, you'll notice that the output of the one on the left is different than the one on the right. The reason for that is relatively straightforward. As I mentioned earlier, the Fourier transform actually computes the dot product between your data and a series of complex waveforms that have both real and imaginary components. And this output is summed. So the more data that you put in, the larger the amplitude you'll get out. So one of the key steps we have to do is scale the output that we get from a Fourier transform so that it's correct relative to our data. And if you think about what that should be at this point, we had a sine wave with an amplitude of 5, so we would like the output of the Fourier transform to also be 5. Now, the output of a Fourier transform gives you a number of coefficients that's equivalent to the number of data points that you put in. Therefore, you have to account for that. You can do that by dividing by the number of points you have. Let's do that and take a look. Now, you'll notice that the amplitude has changed. It is no longer that large amount that it was when we looked at the raw amplitude that was provided. So the scaling has fixed it, but it's not actually the amplitude we'd expect, because if you remember, the input sine wave had an amplitude of 5. There's another problem here, which is we still have those negative frequencies that we've talked about. So let's write some code and try to fix this. So first, what we're going to do is take the absolute value of the Fourier coefficients that are scaled. What this does is remove the imaginary aspect and just keep the magnitude, because that's what we're interested in, the magnitude of the Fourier coefficients. Now, the next step is we want to remove those negative frequencies. We do that by just keeping the positive Fourier coefficients. Now, there's one small trick here. You'll notice that the vector that I'm using here to do this has a +1 at the end. The reason for this is really important. The Fourier transform also gives us amplitude at 0 hertz, which is the absence of a sine wave. And that's the very first frequency bin. So we actually get output that includes 0, then the positive frequencies, and then the negative frequencies. Next, we want to look at the frequency resolution. In this case, it's the sampling rate divided by the number of data points. But remember that your frequency resolution is entirely dependent on the number of data points that you submit. All right. So the more data you put in, the smaller the frequency resolution you'll have. So we get frequencies from 0 by the frequency resolution to the half of the length of the data in this case. Those are the positive frequencies. Now you might wonder why we only go up to n/2 in terms of frequencies. The reason is that you need at least 2 points to represent a sine wave. Therefore, that is our resolution. Some of you that know a lot about signal processing will realize the relationship with the Nyquist frequency. Now, what you'll notice is we are only seeing the positive frequencies from 0 to 500, which is great. And we're seeing a signal, which looks like it's at 15 hertz. But the problem that we have is the amplitude's still not right. We're getting an amplitude of 2.5, and we should have an amplitude of 5. The reason for this is simple. When the FFT is run, it actually splits the amplitude between the positive and negative frequencies. And because this is a real signal, you can actually just double the amplitude here. You're essentially taking the amplitudes that were given to the negative frequencies and putting them on the positive frequencies. Let's do that with code. So, like I said, we can just literally double the amplitude of the positive Fourier coefficients to correct for what was lost to the negative frequencies. Let's plot and take a look. And what you'll see now is our amplitude of 5 is exactly the same amplitude as the input sine wave. So we have got the correct output. I'll go back to the code and explain a few more things. A lot of people use power when they report the results of a fast Fourier transform. To do that, you just square the correct Fourier coefficients. The other thing you might be interested in is phase. Phase is just the angle between the Fourier coefficients. So it's the angle between the real and imaginary aspects of the Fourier output. So to do this in MATLAB, you can simply take the angle of the Fourier coefficients that are scaled. You do get phases for both the positive and negative frequencies, so you want to remove those. And again, you can double them because you've lost something to the negative frequencies. I hope this has helped you understand the output of a fast Fourier transform in MATLAB. If you'd like to see the source code for this video, it's on my GitHub. And if you'd like to learn more, Michael X. Cohen's the guru on this stuff. Check out his YouTube channel or read his book. It's great. And if you'd like to learn more about what I do, I'm on Twitter, @ThatNeurosciGuy.